Okay, this problem is a little more difficult than problem 1 because we're going to have it's not going to look exactly the same, but it's a good problem to go over. So we've got an electric circuit over here. We're going to go over this quickly here so that we don't have to run into it later. Current is going to be expressed by I, resistance is expressed by R, and L is going to be inductance. And finally, E is our voltage. So we can think of electric currents or circuits as like water going through pipes. It's a good analogy. So the voltage is going to be the water pressure. Alright, so let's read this. When you turn on the switch in an electric circuit, a constant voltage, electrical pressure, E is applied instantaneously to the circuit. This voltage causes an electrical current to flow through the circuit. The current is I equals 0 amperes. It's the unit of current when the switch is turned on at time t equals 0 seconds. So let's write that down. We have I equals 0 at t equals 0. Okay. The part of this voltage that goes into overcoming the electrical resistance of the current is directly proportional to the current I. The proportionality constant R is called the resistance of the current. So we're going to have two parts of this current here, or voltage, sorry. We're going to call this, I'm just going to call this first part E1. Let's call it ER. Part that's due to the resistance, or the resistive voltage. So it says that that part is directly proportional to the current, and with the proportionality constant R. So we've got Ri. That would be directly proportional with proportionality constant R. The rest of the voltage, we're going to have another bit here. Rest of the voltage is used to get the current moving through the circuit in the first place and varies directly with the instantaneous rate of change of the current with respect to time. The constant for this proportionality, L, is called the inductance of the circuit. We're going to call this EL since it's the inductive voltage. It says that it's directly proportional to the instantaneous rate of change of the current with respect to time. The instantaneous rate of change of the current with respect to time is di dt, which is the derivative of I with respect to t, and we know that it said proportionality constant is L. So we have that. That's the information from the paragraph. That's basically all it says. And then this is the circuit. Alright, so part A says, write a differential equation stating that E is the sum of the resistive voltage and the inductive voltage. So it's saying E is equal to the sum of the resistive voltage, which we said was ER, and the inductive voltage, which is EL. So I can just write that here. We're just going to substitute that information in. So E is equal to Ri plus L di dt. Not too bad at all. And we're done with A. Alright, going on. Solve this differential equation subject to the initial condition that I equals 0 when t equals 0. Write the resulting equation with I as a function of t. Alright, so we had this before. Ri plus di dt. Oops, there's an L in there, don't I? Plus L. Okay, so now we want to solve this, and what's the only tool we really have right now is to split this up into using separation of variables. So I'm going to take di to one side of the equation and dt to the other side. So in order to do that, let's bring all these constants over to one side. So I'm going to subtract Ri over. Well, I is not constant, sorry about that. Bring all this other stuff over. So I can just have di dt on one side by itself. Di dt, not d. dt. Okay. So let's see here. What if I bring this I, because I need the I to go with the di here, if I divide this over and multiply the dt over. So if let me swap this around so I can have my i's on the left. So I'm just rewriting this here. Okay, so what I'm going to do is I'm going to bring the dt over here by multiplying each side by it, and I'm also going to divide each side by this bit. So we're going to end up then with L divided by E minus Ri di, if di sticks around, equals dt. The dt gets brought over. Okay, now we can integrate each side to solve this differential equation. So I'm going to cover stuff up. We'll just write it up here. Okay, so integrating each side. Okay, the right's easy. But the left here, we've seen in the past that this is kind of always going to be natural log, and this is no different. So the bottom here, we want to do natural log of that bottom bit. But in order to do that, I have to have the derivative up in the numerator up here. So the derivative of the bottom part would be negative r. So I need to put in a negative r up here. But in order to put in a negative r up there, I also have to divide by negative r, because we don't want to change the equation at all. So if I rewrite my equation here, I'm going to bring this L. This L is just a constant, so I'm going to bring that out front here. So we now have negative L over r out in front of our integral. Our negative r in here, because we wanted the derivative on top. E minus Ri di equals the integral of dt. Now we can write this as the natural log of the absolute value of E minus Ri. This bit up in front just sticks around. It's a constant factor, so we got negative Lr, natural log of E minus Ri. Don't forget the absolute value. And the integral of t would be of dt would be t plus c. Great. Okay, so we're gonna need to solve for I now. We want I as a function of t. So let's do that. Ugh, this is gonna be a mess. Alright, let's isolate the natural log first. So I'm gonna multiply both sides by this term here. Or by the reciprocal of that term, sorry. So we're going to multiply both sides by negative r divided by L. So I can put this natural log by itself. So t times negative r divided by L is going to be that. Sorry. This is a t. I'm supposed to curly those, I forgot. And then c times negative RL as well. We got that. Now we can exponentiate each side. Get rid of our natural log. And we will get the inside bit of the natural log equals the other part raised up here, so e to the negative r L t minus r over LC. And using properties of exponents, I can rewrite that as so. constant here. Great. So now this bit here, notice, this is just some other constant. I'll call that C1. So we've got right now then, I'm going to write over here. That takes up too much space. I'll just write over here. We're going to have E minus Ri equals then C1 e to the negative R over L times T. Okay. And we're almost done. We just need to get I by itself. So I'm going to subtract this E over. Get this. It's going to take some getting used to writing that. Minus E. And then divide by negative R to get I by itself. So when I divide by negative R, I can actually swap these around. I'm going to put this as, I'll do this as negative for now. Okay. The negative, I could just distribute that inside and swap those around. So we'll get I equals 1 over R E minus C1 e to the negative R divided by L T. And there we go. We've got I by itself. If we go back and look at what we need here, we want to use that I equals 0 when t equals 0. So let's do that here at the end. So I equals 0 when t equals 0. This is our general form here, but we want to get a particular solution. So I equals 0 at t equals 0. So if I plug that in, I'm going to have 0 equals 1 over R E minus C1 e to the, if t equals 0 up here, the whole thing is going to be 0, so e to the 0. So I could have then, this would be the same as 1 over R times e minus c, because e to the 0, C1, e to the 0 is just 1. Okay, so that's equal to 0. I can multiply both sides by R. 0 times R is still 0. So it looks like C1 equals E. And therefore, we have our equation then. This should look a little familiar, this kind of outcome here. It's almost the same as what happened in problem 1, if we've done that one yet. So we've got e to the negative, sorry about that, negative r divided by L t. Look at that, I remember this time. So that is r, or I as a function of t. Okay. Let's go on to C. Suppose that the current has a resistance of 10 ohms. So we know that R equals 10 ohms. This is omega. It stands for ohms. And the inductance of 20 henries. So 20 is L. If the circuit is connected to a normal 110 volt outlet, this is kind of interesting. I thought that outlets were 120 volts. I don't know. So that means if it's connected to voltage, volts are the unit of voltage, so we know then that E is equal to 110. Write the particular equation and plot the graph. Sketch the result and show any asymptotes. So recall from before, we had this. Right? Double check. Yep. Good. Okay. Now we can just plug this information in here and find the particular equation. So since I is a function of time, I'm going to write it like this. I of t, curly, equals 1 over r, which is 10, you know r is 10, times e, which is 110, minus e, 110, times e to the negative r, which is 10 over L, which is 20, t. Let's simplify this. So I of t equals, I'm going to pull this 110 out, since it's in each there, factor it out. 1 minus e to the negative 10 divided by 20, so that's going to be negative 1/2. Finally, 110 divided by 10 is just going to be 11. There we go. That's our particular equation. So let me plot that here really quick. So this is Mathematica. And we're going to plot, we're going to plot that function here. Okay, so we're going to make some function called I of t. And it is equal to 11 times 1 minus e to the, this top graph here is from problem 1. I can get rid of that. Okay, 1 minus e to the negative 1/2 times t. Make this a little better here. We'll do that from t to, what should we do it from? T equals 0 to 10? Why not? So it doesn't look like what I've done. Okay. I forgot. Okay. Plot I of t from t equals 0. That's what I did on to 10. Oh, I forgot a parenthesis. There we go. Oh, they don't like this. Let's do lowercase I then. Okay. Sorry about all this. There we go. There's our graph. So I can copy this and paste it down here. Or not. Anyway, we'll just look at it here. Look at that. Isn't that a great graph? Wonderful. Beautiful. Okay, so we can see that it's evening out. Let's go on to the next problem. So we've got part D now. Predict the current for these times. 1 second after the switch is turned on. 10 seconds after the switch is turned on. At a steady state after many seconds. Okay, I'm going to just copy this over. Hopefully. I'll just get rid of the top part. Great. This is our particular equation. For this problem, we're just going to plug in t equals these values. So for I, for this one, we're just going to plug in 1 for t. 11 times 1 minus e to the negative 1/2 times 1. Alright, let me figure out what that is real quick. So it looks like that is 4.328. For 10 seconds, we're going to do the same thing. Really quick here, times 10, that's going to be 10.926 about. And for 3, they're asking us at a steady state after how many seconds. So what they want for that then is to for us to find when the current is constant. So let's see. After many seconds, we're just going to find the limit. Let's just take the limit as t approaches infinity. Let's see what happens there. If I'm taking the limit as t approaches infinity of this equation here, 1 minus e to the 1/2 t. We're going to have minus e to the negative 1/2 times infinity, which is going to be just negative infinity. So e to the negative infinity, that's going to be 0. So 11 times 1 minus 0. Looks like that's going to be 11. So at some point, it's going to approach 11 amps and just kind of stay there. So now they're asking us in part E here, at what time t will the current reach 95% of its steady state value? So this is its steady state value. 11 is a steady state value. So what's 95% of 11? So 0.95 times 11. That is going to be 10.45. We want the current to equal 10.45. Let us do that. 10.45, we want to find when t is going to be equal to that. So 11 times 1 minus e to the negative 1/2 t. Realize this video is getting long, I apologize for that. I don't think the problem should take you guys nearly as long if you're not explaining things. Now if I divide 11 over, you get 0.95, isn't that convenient? Okay, so that's going to equal 1 minus e to the negative 1/2 t. Subtract that 1 over, you get negative 0.05 equals negative e to the negative 1/2 t. Dividing by negative, we're going to get 0.05 e to the negative 1/2 t. Okay, I want to get rid of the e, so I'm going to have to take the natural log of each side. Natural log of 0.05 equals natural log of e to the negative 1/2 t would just be negative 1/2 t. So then I can just multiply both sides by negative 2. So we'll get t equals negative 2 ln of 0.05, which is about, let's see, 5.99, and then 1. So after 5.991 seconds, it will reach 95% of its steady state value. And that's all we had to do. So that is problem 3.